The heights in meters and the arm spans in meters of a sample of adults were measured. If x is the height and y is the arm span, the data is recorded as a number of couples x, y, which are given below. Show this data on a scatter plot. So we start off by drawing our x-axis and our y-axis. So remember, the x-axis is the height in meters and the y-axis is the arm span in meters. So the first couple we have is 1.72 for the x value and 1.68 for the y value. So we go to 1.72 on our x-axis, which is about here. And we go to 1.68 on our y-axis, which is about here. So we go up and across until we meet, and we see that this would be our coordinate here for 1.72, 1.68. So 1.72, 1.68. Our next couple is 1.65, 1.66. So 1.65 on the x-axis, 1.66 on the y-axis, and there we plot our point. And we continue on like this for the rest of our couples. And as you can see, all the black dots, this green dot and the red dot, all together make up our set of couples. Part 2. Describe the type of correlation that exists between height and arm span for the data obtained. So from the positions of the data points, there is strong positive correlation between x and y. So first of all, the correlation is strong because if we draw in the line of best fit, we can see that the points are all quite close to it. It's positive because it's going uphill. So we read a graph like we read a book from left to right, so we can see it's going uphill, so it has a positive slope. The line of best fit has a positive slope, so there's positive correlation. Part 3. Calculate the mean of the heights x bar and the mean of the arm spans y bar. Give your answers correct to 3 decimal places. So we let x bar be the mean of the x values, then 1.72 plus 1.65 plus 1.85 plus 1.62 plus 1.70 plus 1.83 plus 1.58 plus 1.92 plus 1.75 plus 1.72 plus 1.63 plus 1.84. So we take all the x values, we add them together, and we get 20.81, and we divide by 12 because there was 12 altogether, and that gives us 1.734. So x bar, or the mean of the x values, is 1.734. We let y bar be the mean of the y values, then 1.68, that's the first y value, plus 1.66, that's the second y value, plus, and then we add all the other y values, and we end up getting 20.35. Again, we divide by 12 because there was 12 y values in total, and we get 1.696. So this is the mean of y values, or this is y bar. Part 4. Draw the line of best fit for the data. Now, to draw a very accurate line of best fit, you have to include the point x bar, y bar, which is the mean of x and the mean of y. So we worked this out in the previous question, part 3, to be 1.734 for the x and 1.696 for the y. So we find that point, so we go across to 1.734 on the x-axis, which is about here, and we go up to 1.696 on the y-axis, which is about here. And we see that this point here is the mean. So you can see it's highlighted in red. So the line of best fit must go through this point. So the point x bar, y bar is 1.734, 1.696 must lie on the line of best fit. This is shown on the scatter plot as the point M in red. By considering all lines through this point and trying to have roughly equal distances to the line for both points on both sides, we can draw the line of best fit as the blue line on the scatter plot. So the best thing to do is to get your ruler and turn it on its side and have the center of the ruler going through this point, and swivel the ruler, rotated clockwise and anti-clockwise, making sure that the center point goes through this point, until you have it in a position where you think the points are equidistant or of equal distance from the ruler itself, and then you can draw on the line. So this blue line here is the line of best fit. Part 5. Use the line of best fit to predict the arm span of a person of a height of 1.87 meters. To use the scatter plot to estimate the arm span, which is y, of a person with a height, which is x, of 1.87, we go vertically up from 1.87 to the line of best fit, and then horizontally across to the y-axis. This is shown on the scatter plot. So we go to 1.87, which is here. We draw a line up until we touch our line of best fit. Then we draw a line across and we end up at 1.80. Predicted arm span of a person of a height of 1.87 meters is 1.80 meters. Part 4. By choosing 2 points on the line of best fit, find the slope and the equation of the line of best fit. We will take the points labelled A and B on the line of best fit because they are far apart and they can be easily read off the scatter plot. So the point A that we've drawn in on the line of best fit is in green, and this is the point 1.60 for the x value and 1.60 for the y value. It's just a coincidence that its x and y values are the same. Then the point B, which is on the other end of the line of best fit, we can see is the point 1.90 and 1.82. So the point A is 1.6, 1.6. We're going to let this be x1, y1. And the point B is 1.9, 1.82. We're going to let this be x2, y2. Then we can calculate the slope and the equation of the line of best fit. So the slope, m, is equal to y2 minus y1 divided by x2 minus x1, which is going to be 1.82 minus 1.6 divided by 1.9 minus 1.6, which gives us 0.733. And then the equation formula, y minus y1 equals m times x minus x1. So substituting the x1 and y1 points in, we end up with y minus 1.6 is equal to, and subbing in the m, the slope, 0.733 times x minus 1.6. This gives us y minus 1.6 equals 0.733x minus 1.1728. And solving for y, so rearranging to get the y on its own, we get y equals 0.733x plus 0.4272. So this is our estimate for the line of best fit equation. Part 7. Use a calculator to find the exact equation of the line of best fit. So entering the data into a calculator, we get A is equal to 0.4002 and B is equal to 0.7471. Thus the equation of the line of best fit is y equals 0.4002 plus 0.7471x. So this is how we use a calculator, or a Casio, specifically a Casio calculator, to find the line of best fit. The same data entry sequence that was used with a calculator to find the correlation coefficient can also be used to obtain the equation of line of best fit. So for Casio FX83ES, we start by pressing mode 2 and 2. This will display 2 columns called X and Y and waits for you to enter your data. After entering each number, press equals. It is easier to enter the X values first and then use the arrows to go back to the top and enter the Y values. When all values have been entered and checked, you can press on, which will clear the display. The Casio FX83ES assumes that the equation of the line of best fit is y equals a plus bx, where a is the y-intercept, i.e. where the line cuts the y-axis, and b is the slope. After entering the paired data, we can press Shift 1 7 and 1 equals for the a value, which is going to be the y-intercept, and 2 equals for the b value, which will be the slope. Part 8. What does the slope of the line of best fit tell us about the data? So in the previous question, we got the line of best fit to be y equals 0.4002 plus 0.7471x. So this is what we got the slope to be. The slope of the line of best fit tells us the rate of change of y as x changes. In this case, for every centimetre that x increases, we would predict y to increase by 0.7471 centimetres using the calculated value. Part 9. If a very tall person of a height 2.02 metres is measured, use the line of best fit to predict their arm span. Is this interpolation or extrapolation? And give a reason. So again, the line of best fit that we came up with from the calculator is y equals 0.4002 plus 0.7471x. So if x is equal to 2.02, we can use the equation of the line of best fit to predict the value of y. So if x is equal to 2.02, y is equal to 0.733 multiplied by 2.02 plus 0.4272, which equals 1.91. So basically we just swap this x for 2.02 with brackets around it. Thus, we would expect a person of a height of 2.02 metres to have an arm span of 1.91 metres. As 2.02 lies outside the range of the height data given in the table 1.5 to 1.92, predicting the arm span of a person of a height 2.02 metres is extrapolation. So extrapolation, the definition is the extension of a graph, curve or range of values by inferring unknown values from trends in the known data. It is important to realise that the points on a scatter plot may not be modelized best by a line, i.e. they may not be linearly correlated. Some sets of data are better modelled by quadratic or other polynomial curves, or by exponential curve. For example, the data shown on the scatter plot opposite has an OR value of 0.10, demonstrating a very weak linear correlation. But this does not mean that the data is not correlated. In fact, it shows a strong correlation with a quadratic curve. We call this quadratic correlation. On our course, we do not have to be able to work with quadratic or other correlations. It is sufficient to know they exist. When we talk about correlation on our course, we mean linear correlation.